Welcome to lecture number 7 for new N302. Last time we talked about the center of mass reference frame, the center of momentum reference frame. We compared that to what we call the lab reference frame, and that is the observer as one would be watching this experiment take place, or this event take place, this reaction take place. We developed expressions to go back and forth between the two reference frames, whether that be the center of mass or the lab, and we expressed everything in terms of the kinetic energy of the projectile. That's really the thing that we either have control over, or we can at least measure, or have a good estimate of before going into the experiment. And the things we want to measure is the scattering angle and the energies afterwards and that sort of thing. But we can express everything in terms of that EX. And so today we're going to simplify that. Of all the events that could take place, all the reactions that could take place, we're going to focus today on a subset of those, and those are going to be neutron scattering events. This is important to us as nuclear engineers. In a reactor, for example, the neutrons are coming off at a very high energy off of a fission event, and we need to slow those down in order to make them more enabled to induce another fission event. And the parameter that we're going to use to help quantify that is a parameter known as lethargy. We'll introduce that. Eventually we want to understand, okay, how many scattering events do I need to have? And just as a reminder, elastic scattering means that I've got, and especially this neutron, the neutron's coming in, it's colliding with some other nucleus, and nothing's changing from a nuclear standpoint. There is no nuclear reaction. It's just a simple exchange of momentum, and hopefully that neutron comes away at a little less energy, and then we have another scattering event, another one, until the neutron slows down to get in the thermal spectrum where the fission likelihood becomes much higher. By the way, we call these thermal neutrons because they're in thermal equilibrium with their surroundings at that point, or near equilibrium. But we want to be able to characterize that scattering. And we want to know how many times we need to have a scattering event in order to get to energies that we are targeting. And then the last topic that we'll cover today is the parameter that we use to characterize the likelihood of such an event taking place. We might know how many events we need in order to slow it down, but we don't know how often those are going to occur, for example, or how likely they are to occur in this type of target or that type of target. And so we'll introduce the concept of cross-section. We're going to deal with this in a lot greater detail in subsequent lectures. And so today we're just sort of introducing the basics of it. What is it? How is it formulated? What does it mean? How can we make use of it? That sort of thing. So why do we care about neutron scattering? And the answer to that is moderation. We want to, and that is the process of taking the high energy neutron from the fission event and reducing its energy down to something that will induce a fission event. And so the answer to this question is simply, we care about this because we need to moderate. We need the moderation, at least for thermal spectrum reactors. And so we have low energy neutrons are going to are going to be better able to induce fission. But it's the high energy neutrons come from the fission event. And so again, we want to understand what it takes in order to moderate those down to these thermal levels. And so we're going to do that through elastic scattering primarily. And we're going to take, again, of all the reactions that could take place, we're looking at specifically a neutron as the projectile, and then different targets on the reactant side And then on the product side, we have that neutron again, because it's just a scattering event, and that same target. So in such a scenario, my Q value in an elastic scattering event, my Q value is going to be 0. I don't have any change of mass. I don't have any nuclear reactions actually taking place. So this is what we're always going to have for any elastic scattering. Whether it's a neutron as a projectile or not, if it's elastic scattering, Q value is 0. But in this case, because it's a neutron as a projectile, mx equals my equals mn. The mass of the neutron is what the projectile is, and the light particle is after the scattering event. And likewise, my target before is the same thing as the mass of my heavy product after the event. And so there is no nuclear reaction. X equals Y, capital X equals capital Y. And let's just write this down, 1.008665 AMU. So that's the mass of my projectile. That's the mass of the neutron, obviously before and after, since there's no exchange in mass. And so we're going to take these expressions that we developed last time for energies in the center of mass reference frame and in the lab reference frame, the angle in the lab reference frame, and we want to simplify these for the scenario that we're encountering in this lecture right now, and namely elastic scattering with a neutron, specifically with a neutron as our projectile. So in this case, what we can do is we can say that the mass of our projectile is approximately 1. So we got 1 and some change, 1.008 and some change, but we can approximate this as a value of 1. And likewise, we can approximate this as a value of the mass number, how many ever nucleons it has, and the numerator likewise. And so this then just becomes A over 1 plus A quantity squared times EX. And there might be a part of your brain that has problems with this, because after all, when we first introduced the Q value, it was stressed that you need to include many digits of precision on these mass values. Why in the world now are we able to just approximate them like we are? And the answer to that is because back then we're looking at differences in mass. We got the reactant's mass, we got the product's mass, and the difference between them is really small. And because that difference is small, we need to include all those digits of precision. But in this case, we're taking ratios, we're adding them together, and this isn't as sensitive to all those digits of precision. And more importantly, we get I wouldn't even say a rough estimate, but a very good estimate of the ability that different targets have to perform that moderation, to slow down the neutron by looking at different targets of different mass numbers. And so that's what we're doing with all these expressions, is we're replacing our masses with either A for the large particles or a value of 1 for the small particles. So this then becomes 1, this becomes A, this becomes 1, that becomes A. And we're left with A over 1 plus A squared. And these are all, just like they were before, they're expressed in terms of the energy of that neutron coming in. So that's my projectile energy, that EX. And then notice these are all in the center of mass reference frame. So I'm going to now look at the energy in the center of mass reference frame, the energy of the neutron after it is come from that collision. So that's what my EYC is. So this here is A, this is also A, this is 1. My Q value in this case, as we said before, because it's elastic scattering, my Q value is 0. And I got this is 1, this is A, and this is 1. And I find that this is just going to be A over 1 plus A squared EX. And you see that it is the same as this one. So this is my energy. The top one is my energy of the neutron coming in, and the bottom one, this other green one, is the energy of the neutron leaving. And if we're talking about slowing neutrons down, then it might be a little disconcerting to see that my energy, at least apparently, didn't change. And the answer to that concern is that that's in the center of mass reference frame. We're going to deal with the lab reference frame in just a minute, and we'll see that indeed I do have that decrease in energy. But if I'm talking center of mass reference frame, if you remember before and after the collision, I choose my reference frame such that the net momentum is 0. And so in that reference frame, if my net momentum is 0 and I only have two particles that are colliding, and if the mass of this one before is the same as the mass of that one after, and the mass of the heavy one is the same as the mass of the heavy one after, then I have no choice but to force those. Since the masses are equal, those velocities have to be equal, and the momentums have to be equal. I should have said that in a different order. Since the masses are equal, and the momentum has to be equal, then the velocities also have to be equal. And if mass and velocity is the same before and after, then guess what? Energy is the same before and after. But again, don't get concerned because this is in the center of mass reference frame. And again, just in a minute, we'll see the difference between that and the lab reference frame. So finally, I've got my heavy particle. This is 1, this is A, this is 1, Q is 0, 1, A, and 1. And I'll find out that this is 1 over, or A over A, 1 plus A squared times EX. And this, not surprising, is equal to what we found for the heavy particle before. The heavy particle after and the heavy particle before have the same kinetic energy when expressed in the center of mass reference frame. And the light particle before and the light particle after have the same kinetic energy when expressed in the center of mass reference frame. All right, let's go to the lab reference frame now. We're looking at EY. We knew that just a minute ago we found an expression for this. This EY in the C reference frame is just going to be A over 1 plus A quantity squared. EX, this is 1. This is also 1. We have A and we have 1. And then over here we've got the center of mass reference frame, that scattering angle. So we're going to leave that one alone. That's going to be our input. EX and that phi sub C are going to be the two inputs we have into this analysis that we're about to do. So, but this one is heavy, so it's A. This is light, so it's 1. This is 1, that's 1. And then this is what we found before, squared EX. And so I've got myself an EX in every term, and over here I've got an EX, so I square that, then I take the square root, so I've got an EX in all those terms. And then I've got a 1 and a 1 underneath this radical, and then so I've got, the only thing that's left under the radical is A over 1 plus A quantity squared, take the square root, and so I end up having EY over EX equal to A squared plus 1 plus 2A times cosine of phi sub C over 1 plus A squared. And so this represents now in the lab reference frame the relative decrease in my kinetic energy of that neutron, because these are the light particles before and after. So I could express this in terms of energy of the neutron after and energy of the neutron before. And so this ratio is always going to be less than 1. And we can prove that to ourselves by looking at the numerator versus the denominator. If I have cosine of phi, that angle, as the smallest that cosine argument could be is -1, the largest it could be is +1. And so if I make that phi of c equal to 0. This is analogous to me coming in and hardly changing that angle at all. It's going out almost at the same angle. So you can think of this almost like a billiard ball just sort of kissing the other ball just ever so slightly, and the trajectory of that the moving projectile is not really altered at all. And so we call this a glancing interaction. And if that's the case, in the numerator now I've got a squared plus 2a plus 1. Well, what is that? It's just 1 plus a quantity squared, and so my ratio becomes 1. And that makes sense. If I have a 0 degree scattering angle, then I'm not really changing energy that much at all. The closer I am to 0, the smaller that energy exchange is, and so the ratio of my neutron energy before to after should be approximately equal to 1, and that's exactly what we see. Okay, so the next one we want to look at is the large particle on the product side. And so this one we've got Q equals 0. We've got an expression now for EY, which is right here. And that'll be in terms of EX. And then I've just got EX there. And so I find that EY over EX equals 2a times 1 minus the cosine of phi sub c divided by 1 plus a squared. And so now I know the relative change in the kinetic energy of the target of the large particle. And the last one, these are the equations we really care about here. And the last one I want is a relationship between the scattering angle in the center of mass frame and the scattering angle in the lab frame. And so how do I get to that? I just use this expression here. I know I have a value for EY in the center mass reference frame. I have an expression for EY in the lab reference frame. And so this just becomes 1 minus EY in the center of mass reference frame was a squared 1 plus a quantity squared. That's and I'm going to have an EX over here. That's my EY C. My EY is going to be equal to 1. I'm going to divide this, so I've got 1 plus a squared over a squared plus 1 plus 2a cosine. Move these guys over. 2a cosine of phi c. And that's also going to be multiplied by EX. And then I've got that minus the cosine squared of phi c sub c. So this cancels out here, my EX cancels out here, and I'm left with, after I take the square root of this, because I got the cosine squared on the left-hand side, then I find out that the cosine of phi simply equals 1 plus a, that's the cosine of phi sub c, over a squared plus 1 plus 2a. That is going to be to the 1/2 power. And so now I've got expressions that as inputs will take the kinetic energy of the neutron coming into the scattering event, so that's EX or EN. And then I've got the energy leaving, what the neutron is leaving that interaction, and what the heavy particle is leaving that interaction. And I know what the lab scattering angle is. And so each of these are functions of EX, they're functions of phi sub c. Phi sub c, if you recall, we're going to take that from 0 to pi. But they're also functions of that A, so the mass number of the target. And so if I choose a lighter particle versus a heavier particle for that target, then I'll get different responses, different behaviors for that change in kinetic energy. The energy exchange is going to be dependent on not just phi sub c, but also the mass number of that target. So let's go to example number 1 to demonstrate this. So in this example, we want to evaluate the lab system neutron and target scattering energies. So in the lab system, that means we're talking about lab system neutron is going to be EY, that's the scattered one. Or I could express this as EN after the event. And then the target is going to be E capital Y. Or I could express this in terms of E capital X after the event, because again, there is no mass exchange there. No neutrons or protons are moving spots. We have the same particles before and after. And we find their dependence on the scattering angle in the center of mass reference frame. So scattering angle in the center of mass reference frame, that is phi sub c. And we want to present the results in graphical form. We want to take, as we've done in the past, we want to go from 0 to 180. And we want to plot phi on the x-axis. And we want to compare that to this here, which represents my energy decrease, a relative energy decrease in the neutron. And I want to consider 1, 2, 3, 4, 5, 6, 7 different targets. They all have different mass numbers, and so I'm going from very light to relatively very heavy. And I want to have 7 of those curves on the plot. And then I do this again for this parameter here, which is the relative increase in the target nucleus kinetic energy. Okay, so since we're going to be repeating this for many times, we've got 7 different mass numbers to consider for the target. We've got a whole range of data points to consider for phi sub c, and so it's going to be in our best interest to do this with some code. And so we'll go to the code for this, and I'll first show you the function for this. You notice the inputs to this are going to be the mass number of my target and the phi sub c. And my outputs of this function are going to be phi, so my scattering angle in the lab reference frame. And then this represents the relative decrease in the kinetic energy of the neutron, and this is the relative increase in the kinetic energy of the target. And so these expressions here are just exactly what we just wrote on our notes. There's nothing different, just typing it in. And so I can now call this function how many ever times I want to, and that's what I'm doing in this script here. I list the values of A from the problem statement, 1, 2, 7, 10, 16, 56, 235. And then I create a vector for this phi sub c, and you notice I'm going from 0 to pi, and I'm stepping in 1/100th of a step between the beginning and end, so I'm going to have 101 data points there. And here I'm just creating space, not that I necessarily need to in this, these are small matrices, but I want to store for each one of the unique phi sub c and a inputs. I want to be able to calculate that independently, calling that function down here like I am. And you notice I'm stepping through in I, and I'm stepping through in j. So I is in reference to a, so that's going to step 1 through 7 in each of these values here, and then j is going to go from 1 to, in this case, 101, because I've got a vector that's 101 elements long. And I just output and start building these matrices. And as soon as I'm gone through a single, so this represents one a value, and I've gone through the entire vector of phi sub c, I'm going to plot those results. And I'm going to repeat that again and again for each value of a. So I've got 2 figures going to pop up here. I'm plotting phi. I'm converting here to degrees from radians. And in the first one, I'm plotting that relative decrease in kinetic energy of the neutron. And in the second one, I'm plotting the relative increase of kinetic energy in the target. And then I just tidy them up, put a legend on there, labels on the axes, that sort of thing. So when I run this, I get, oops. I get values. I get the 7 different curves here, all labeled properly. And you can see we'll start with the largest mass number. So if I have a large mass number, that's this curve at the top here, then the ratio of my neutron before to or after to before is a little less than 1, but it's approximately 1. So over here I've got a ratio of 0.98 or so. So that means that I decreased the energy just by 2%. The neutron coming in versus the neutron going out only changed by 2%. And likewise over here, this one is less than 2% because its mass is bigger. This is the target. But when I have a large target, then I don't, no matter what I do in terms of that scattering angle, I don't really see a lot of energy exchange between the two. And in fact, in the ratio of an extremely large mass number, as it goes to infinity, I would see no change. And as I decrease that mass number, I get a little bit more and more energy exchange. So the lower this curve goes, then the lower this number is, and the more energy transfer I was able to achieve between the neutron and the target. And so it's in my best interest to choose targets that have low mass numbers. And you can see here, the best I could ever do is when I have a phi of 180. So 180 in each of these cases, with the exception of a equals 1. We'll talk about that in just a minute. But anything from a equals 2 or higher, then the most energy exchange happens when phi is equal to 180 degrees. So what does that mean? That means this is a head-on collision. The neutron's coming in, and it's going right back from where it came from. And so that's the most energy exchange that I could ever have between these two objects. And you see that the biggest energy increase, likewise to the target, is also around or at 180 degrees. So let's talk a little bit more about a equals 1. So a equals 1 stops at 90 degrees. And so what does a equal 1 mean? It means that the mass of the thing that is the target is the same as my neutron. They both have atomic mass of 1 AMU. And so if it's the same mass coming in, what's happening, this is going to be similar to like Newton's cradle, where you let the ball, there's a series of 4 spheres or so, or 5 spheres that are all touching. You lift one up and it transfers the energy to the one on the other side, and back and forth and back and forth. And so that's exactly what would be happening here if I have 2 objects of the same mass. One is initially at rest, one is moving with some kinetic energy. It's going to transfer all of that kinetic energy. It's going to then remain completely still. It's transferred all of its energy, so now it's stationary, and all that momentum's traveled to the target in this case. So when talking about a mass number of 1, it only makes sense to consider scattering angles up to 90 degrees, because I can never have a scattering angle of 180, because I can't. A neutron's not going to collide with a neutron or a proton and reverse direction. It's going to then impart that energy to the proton or neutron, and then that one is going to travel downstream a bit. So the largest energy exchange, so aside from atomic or the mass number equal to 1, then the largest energy exchange I can ever hope to have is a head-on collision. That's one takeaway from these figures. The other takeaway is that the lower the mass number is, the more I am able to induce that energy exchange. And the best I can ever induce is if I have a head-on collision. Okay, so let's go back to the notes here. And let's talk a little bit more about these special cases of phi equals 0 and phi equals pi. In fact, let's go back here to the simulations, the coding, and let's make one more plot. In this one, we're going to look at phi as a function of phi c. So let's plot, let's do phi c on the x-axis, and then we'll plot phi on the y-axis. And let's make a legend on that one too. So again, we're going to neglect for just a minute a equals 1. We'll talk about that a little bit more, but you'll see that regardless, so this one on the x-axis is the phi in the center of mass reference frame, and the one on the y-axis, I forgot to multiply it by, convert it to degrees. Okay, so this is mass number 1, and then it gets increasingly higher as we go up here. So for the mass number that is the highest, you see that this is basically a straight line connecting from 0, 0 to 180, 180. So for a very large for a large mass number target, there is no difference between the phase angle, the scattering angle in the lab reference frame, or compared to the scattering angle in the center of mass reference frame. And only when I get to really small mass numbers is there an appreciable change there. But no matter what the mass number is, even for appreciable changes, I am at the two extremes, at 180 and 0, I have the same scattering angle, whether I'm irrespective of which frame I happen to be in. And so if I've got a head-on collision, that's what this data represents here. It is a head-on collision in both reference frames. If I've got a glancing or an almost no interaction, then it's a almost no interaction or a glancing interaction in both frames. So coming back to these special cases then, phi c of 0 and phi c of pi in the special case of forward scatter and then back scatter. This here is going to be what's called a glancing interaction. And at the extreme, when phi sub c is equal to 0, then EY equals EX. And we saw that in the other plots we were looking at just a moment ago. There is no, in this case, there's no interaction. That's what that means. I don't have any energy decrease in the neutron, and I don't have any energy increase in the target. So this one here is going to be a head-on collision. And the expression here, if I substitute phi sub c equal to pi in the expression, then my relative decrease in kinetic energy is going to be equal to the following: a squared plus 1 minus 2a over 1 plus a squared. Now this numerator is the same thing as a minus 1 squared, and this is a plus 1 squared. Right, actually there's a negative 1 in there. Oh, but the negative 1 can be squared, so this, yeah. Right, so I've basically, and the negative 1 squared is 1, so I basically have EY over EX equal to a minus 1 divided by a plus 1. And then that is squared. But this is always greater than 1. always less than 1. This is always going to be less than 1, meaning I'm always going to have that some amount of decrease in kinetic energy. And this is often referred to as the collision parameter. And just to confuse us, the textbook is going to use alpha for that. You think that alpha should be reserved for the alpha particle. So don't get confused by that. This is just a parameter that you might see a couple more times throughout the semester, but what it represents is the best we could ever do, right? The best we could ever do is a head-on collision, and this now is a very concise way of predicting that decrease in kinetic energy as a function of just A, just that mass number of the target. So now let's look at the cases of maximum energy transfer when A equals 1 and A equals infinity. For A equals 1, we talked a little bit about this already, but what would this be? This would be a proton, or it could be hydrogen. In this case, my collision parameter, alpha, if I look at that, it's A minus 1 over A plus 1, then this alpha equals 0. And what that means is that all momentum is transferred and the neutron comes to rest. And EY in this case is going to be 0, and E capital Y is going to be equal to E small x, meaning the energy of the neutron before is now the energy of that target after, because my neutron came to rest. And then when A is infinity, obviously we can't ever get to infinity with a mass number like that, but as we approach it, then what is going to happen to alpha is going to be equal to 1, and EY is equal to EX, meaning no energy loss. The only thing that changes then is the direction is reversed. And so you can think of this case where the neutron's coming into this insanely large nucleus, and it's got so much mass that nothing happens besides the neutron just changes direction. It has the same energy as it did coming in, and it's just got a 180-degree change in direction. So we want to start to get to a point where we can consider or determine how many such collisions we need in order to decrease the energy of the neutron down to levels where, again, we can start to be confident in it inducing another fission event. And so the question is, well, what should I do in terms of that phi sub c? Do I just assume that it's a head-on collision every time? Well, that's probably not going to be super accurate. Do I choose a different value of c? Do I choose 45 or 90? That's kind of the average. And the answer to that is we're going to need to integrate over all the possibilities that phi could be. And so our standard nomenclature here for this, the interactions we've been dealing with, we've got our projectile, we've got our target, and we've got our light product and our heavy product. After the reaction, we've got our scattering angle for both the light and the heavy, and we know that this is going to be between 0 and pi. But we've got this phi sub c here, and again, that's going to affect how much energy decrease I have each collision event. But it's important to recognize just what's on the paper here is just a two-dimensional depiction of that. But I could have, a phi sub c, but I could be out of plane in some direction as well. And that out of plane one can go all the way around. It can go 360 degrees. And so what we'll do to kind of set the stage for this integration that we're talking about, we're going to eventually get to this figure here, but let's simplify it and go back to 2 dimensions and remind ourselves what we know, or maybe we didn't realize the meaning of it ever, but it's important that we do realize that meaning before we try to make sense of the 3-dimensional world. So in 2D, we are going to use, for the angle, we're going to use radians. And radians is unitless. We say it's a unit, but it is indeed unitless. Right? It's not. It's a ratio of a length to a length. And so what this looks like here is, if I have some angle that, let's say, is 1 radian, then what that means is this arc length. The arc length is going to be equal to the radius. When I have an angle of 1 radian, that's exactly what that means, is that my arc length equals the radius. And if I integrate that, the radians over all possible values, I'm going to create a circle basically. And if I integrate that, then I'm going to get a value of 2 pi. And that arc length, if I did integrate that, if I did consider all possible options and all possible domain values for that angle, then that arc length becomes the circumference of the circle. And it's not surprising that the circumference of a circle is 2 pi times that r. So with that kind of as a backdrop, let's go to this 3-dimensional space now. And in 3-dimensional world, we're going to talk about a solid angle. And the solid angle we will call capital omega, and the units for that are steradians. And so it's not just one angle measurement that tells me all the information I need to know in a 3-dimensional world. I need 2 angles. And that's what we're looking at here. We've got phi, and then we've got this azimuthal angle, capital phi. And just like we were concerned in the 2-dimensional world, we're concerned with coming up with an expression for the arc length. In the 3-dimensional world, we're looking at coming up with some understanding of the area that this 3-dimensional, that this solid angle subtends, that it creates on some surface, a distance r away from the origin. And so we're looking at this surface here, this dA, and as I calculate that area, I could express it in terms of the lengths that we see here. dA equals r times d phi multiplied by the side of the other square, or the other side of the square, which would be r times the sine of phi d capital Phi. And that's going to equal r squared sine phi d capital Phi. Right, that's what that infinitesimal area is represented by. And the domain here is going to go from 0 to pi in phi, just like we've done before. And then it'll go from 0 to 2 pi in the azimuthal angle direction. And so what we end up, the way that we quantify this steradian is that we say that dA also equals the, that should be d, sorry. We've got d omega times r squared. And so if we equate this expression with this expression, we can see that my r squareds are going to cancel out. And I've got this d omega equals sine of phi d phi times d capital Phi. So now we can integrate that over some domain. And we will consider the entire domain listed here, and let's see what we get. So the integral of that d omega, the integral of that solid angle, is going to be the integral from 0 to 2 pi of d capital phi and 0 to pi of sine phi d phi. And this right here, if I do that integral, the integral of sine theta or sine phi from 0 to pi is going to equal 2. And so I put this in there, and then I find that my total integral here is going to be equal to 4 pi. And that's really one of is probably the main take-home message from this analysis, that you understand that what we did with our radians in two-dimensional space and found out that the integral of that is going to be 2 pi. We found out that the integral of my solid angle is going to be 4 pi. And if you think about what we just said about our two-dimensional world, we've got the circumference, right? That arc length becomes the circumference. It's 2 pi r. There's the 2 pi. If I look at this in three-dimensional space, I'm now looking at a surface area. And so if I integrate over that entire spherical area, I've got the surface area of a sphere, and that's going to be 4 pi r squared. There's the 4 pi. So what we need to do is integrate over all this space. We need to understand what the tendency is for something to be scattered in this direction or that direction or some other direction. And for a scattering event that is a neutron scattering event, it is just as likely to be in this range of angles as it is in this range of angles, as in this range of angles. And so there's no propensity or dominant direction. We call that an isotropic surface. Like the scattering angle is isotropic. It's independent of that direction. And because of that, we can make use of this integral here and find that 4 pi is going to come back into play here in just a minute. And so the way that we're going to do this is we're going to quantify a new parameter called lethargy. Now, if something's lethargic, it's very slow. A sloth is very lethargic, for instance. But the reason we do this is so that we can express this in terms of the change between two states. If I start out at a value of 5 and I go to a value of 1, or if that's a ratio of 5 there, or if I started out at a value of 50 and I go to 10, that's still a ratio of 5. The change in lethargy, which is what we're looking at here, for those two scenarios would be identical. So for those of you who've had thermodynamics, this is a state variable, this change in lethargy. And so it doesn't matter the path that I take to get from my initial energy state to my final energy state. All that matters is what those energies were at the initial and final state. And so then I can express this change in lethargy. This here is then my ratio of my initial to final energies. And I can express that in terms of the relationships that we just developed that now take phi sub c and A into account. And so this really represents one event, right? This is the change in lethargy for one event, one scattering event. And we were up until now we were expressing that in terms of like the percent change in energy from the neutron and percent increase in the heavy particle of the target. But now we're just going to express it in terms of this lethargy. And as a reminder, this is a function of that scattering angle. And so the answer or the question is, well, what do I do about that? What kind of angles do I consider? And the answer to that question is that I need to just integrate over the entire domain of this solid angle, just like we did before. And that's what we're looking at down here in this next expression, where this Greek letter kasi is the average lethargy change. And so these brackets here represent an average. I'm taking the average of that, meaning I could consider this angle, I could consider that angle, and I'd get a different value for that delta U, for the change in lethargy. But if I do that, you know, a large number of times, I do that experiment a large number of times, I'm going to get all these lethargy values, and they're going to be different. It's going to be a data set. Then I take the average of that, and this is what I get. And so in order to compute that average, we need to integrate over the entire solid angle domain. And that's what we're doing in this numerator. And then we divide by the total solid angle integral there. So this thing here is going to be 4 pi. And so this equals 1 over 4 pi from 0 to 2 pi. And then from 0 to pi of the rest of this, which we're going to plug this in there. So that'll be sine phi sub c, just like we did up here, right? But now we've got to take the metric that we're integrating with. So we got sine phi sub c, and then we got the natural log of all this stuff. 1 plus a squared divided by a squared plus 1 plus 2a times the cosine of phi sub c. So now we've got to perform this integration, and we've got sine, we've got a cosine that we have to be mindful of as we integrate. And the way that you're going to handle this is a u substitution. Let u equal the cosine of phi sub c. Then du is going to be minus sine of phi sub c d phi sub c. And so that's here. Still not without an integral table, probably, or if you're doing this on a daily basis, you probably would have to look it up. But we can do this integral, and there's a healthy amount of algebra to take care of here. But at the end of this, we find out that the average lethargy change, and this now is now accommodating all scattering angles across that entire solid angle domain, is going to be 1 minus a minus 1 squared, a plus 1 over a minus 1. So now, again, this is for one event, and this just says on average, this is what I expect to see in terms of that lethargy. If I do it 100 times and I find the average lethargy change, then this is what I expect to see. And so now we ask ourselves, well, what happens when we have multiple collisions? Now that we've quantified the average lethargy change, let's add all those up. And if I know how many events I had, then this is going to be approximately equal to the number of events times that average lethargy change. And that's going to equal my total lethargy change from the very beginning to the very end. And that's just going to be the natural log of my initial neutron energy to my final neutron energy. And so, for instance, now if I'm talking about a fission event, I know what the energy is coming out of the fission of that neutron, and I know what I need to moderate it down to. And so I know both of those values, the numerator and the denominator. I know the total lethargy change. And I can find out what the average, well, let me solve this first. So what we're going to do is we're going to set this expression and this expression. And we're going to solve for that n. And so n is approximately going to be equal to 1 over that Kasi times the natural log of the ratio of these guys. So I know the number, I know the average, which I'm going to get from here. That's just a function of the mass number of the target. So if I know that, and I know my final state of the neutron, and I know my initial state of the neutron, I know my initial state and I know my target final state, then I can estimate how many collisions I need in order for that moderation to take place. And then I can look at that as a function of the moderator. If I'm using hydrogen, if I'm using graphite, which is carbon, if I'm using this or that, I can see how many collisions it's going to take to get there. So let's do a quick example on that topic, and then we'll hit this final topic of cross-section here in a minute. So for example 7.2, we want to look at the average number of elastic collisions. This is our N. Required to thermalize, so that is going to be our E final. A fission neutron, that is our E initial. And in this case, we're looking at potassium-39 as our target, and so we have A equal to 39. So we can easily just calculate the average lethargy change for A equals 39. This C is going to be 1 minus A minus 1 squared over 2A times natural log of A plus 1 over A minus 1. It's going to be 1 minus 38 squared over 78 times the natural log of 40 divided by 38. When we do this calculation, we'll find a value of 0.05. And then we can estimate the number of collisions that it's going to take from this equation. Initial over E final equals 1 over 0.05 times the natural log of 2 MeV, so that's 2 times 10 to the 6th eV over 0.025 eV. So my units cancel out there, and I'm left with 363.95. And so N is going to be about 364 collisions. So if I'm using potassium-39 and I want to thermalize all the way from 2 MeV down to basically 25 millieV, then it's going to take me 365 on average, it's going to take me 365 collisions. Now, if I happen to get lucky and I have a bunch of head-on collisions, it's going to be less than that. But on average, that's what I'm looking at for potassium-39. And I could repeat this for other targets. I can look at all the way up to uranium or anything I want to, for that matter. And because we integrated over the entire domain of that solid angle, we're getting an estimate of the average behavior for any one event. And obviously we're not going to get exactly the average every time, but if we do enough of those events, then that is going to be the average value. And in a real situation, we're never dealing with one neutron and one target. We're dealing with 10 to the 20 or 10 to the 15, or this huge amount of neutrons and huge amount of target nuclei in the solid. And so that's the next topic that we're going to cover, is trying to answer the question, well, that's nice that we now know the number of collisions, but I still don't know anything about how often those collisions are going to take place. So I don't know how long it's going to take me to get those 364 collisions in the potassium, as an example. And I don't know, it couldn't possibly be the scenario where I shoot in this many neutrons and they all have interactions. It's going to be a very small fraction of the neutrons that are coming into a domain that actually undergo some sort of reaction. And how do we account for that? And the answer to that is to look at this this parameter called cross-section. So this is going to be related to the probability of any event taking place, like scattering, for example. So to illustrate this, we're going to consider some neutron beam here. And the parameters we need to describe it, we're going to assume that they're all the same speed, and they're in one direction only. And so the parameters we need to describe this are going to be our beam density, and that's going to be some number over a volume. And in these analyses, we almost exclusively use the length scale of centimeters. So it's some number, and that's going to be, in this case, number of neutrons. Actually, I got to move that because we're going to have some target, and it's going to be very thin. Oh, we forgot one more. So we have the velocity of those, so the beam velocity. So that's going to be in units of centimeters per second. So the product of those two are going to be what's known as my neutron flux. If I take the beam density, multiply by my beam speed, then I get some number of neutrons per unit area per unit time. So it's how many neutrons are passing through every second over this unit cross-sectional area. And so what we want to know in all of this, we want to know is the reaction rate. We'll use capital R for that. And so that's going to be number of reactions every second. That's what we want to know. We know how many potential reactions we could have. This many neutrons are flying through the domain. And we know that the actual reaction rate, how many of those neutrons are going to undergo some sort of event, is going to be a small fraction of the ones that we're sending in. But that's what we want to know. We want to know the reaction rate. And so this will be in units of some number per second as well. And that number in this case is not neutrons, it's not atoms, it's the number of reactions. But in order to characterize this surface, our target here, we need N, which is going to be our atom density. And that's going to be some number over a unit volume. In this case, this is going to be number of atoms. We need to know the cross-sectional area, and we need to know the thickness. This will have units of area, obviously, and then the thickness. The target cross-sectional area and the thickness of that target. And so if I multiply those three parameters together, I've got atom density, I've got cross-sectional area. Cross-sectional area and thickness multiplied together are my volume, and I've got atom density as number of atoms per volume. Multiply that together, I get the total number of atoms in that volume. And so as I look at reaction rate now, and I ask myself, well, this is going to be a function of the beam quantities. Again, these two together are my neutron flux. And then I'm going to take the target parameters, Na and delta X, and if I do all three of those together, this is the number of atoms in the target. And I look at the units for these. This one's going to be neutrons per centimeter squared per second. And this one's going to be atoms, total just number of atoms. And so what do I need in order to get this into a reaction, number of reactions per second? Well, I just need to get rid of this area here. And if I have one more parameter over here, we're going to call this sigma. that has units of centimeters squared, has units of area, then this will then cancel with my area unit here. This is called the cross section, and this is a material dependent number. This is going to be dependent on the neutron, the energy that the neutrons are at. We talked a little bit about fission being sensitive to the propensity of a neutron to induce fission is going to be dependent on the energy of that neutron. That's why we have to slow them down. It's going to be dependent on all these things, but if we figure out what the cross section is, it's going to have units of area, so centimeters squared. And the formal definition of this is to look at the limit as that delta x goes to 0. So as the thickness of that target gets smaller and smaller and smaller, the limit as it goes to 0 of how many reactions I have over the beam parameters, so NB and VB, and then the target parameters. And so if I was trying to measure cross-section, this is how I would do it. I would measure the reaction rate. I would know parameters about the beams coming in, and I would know enough information about the target. So let's go to a quick example here, and then we're going to explore some data files. So here in example 7.3, we're looking at a slab of aluminum, in this case aluminum 27. We know the thickness, that's our delta X. This is, by the way, basically 100% of the naturally occurring aluminum in this world, aluminum 27. So we know delta X, we know the cross-sectional area, so we know the volume of that aluminum target. We know the neutron beam passes this many neutrons per second through that target, and we know the reaction rate. So this is going to be R, and this one is not going to be either of those two. It's going to be the product of N and B and VB and A. Right, so NB and VB is going to be my neutron flux, and then if I multiply that by area, then that's going to give me my neutrons per second that I've been given there. So the question is, what is the interaction probability? And then we want to find the microscopic cross-section. Now, we haven't talked about this word yet, but we're going to next lecture, microscopic versus macroscopic cross-section. What we're dealing with today is the microscopic cross-section. So we want to know what that is for the aluminum. Now, in this example, we're kind of working backwards to what the reality of it would be. We typically want to measure. We typically have the cross-section data, and I'll show you that in just a minute. But we will typically do that. We use that information to then predict how many reactions we're going to have, whether that be a fission reaction or a scattering reaction or whatnot. But the first question is, what is the interaction probability? So the probability is going to be defined as the number of things that are happening, the rate at which they're happening, divided by the potential rate at which they could be happening. And the rate at which they could be happening is how many neutrons I'm sending in there every second. And the rate at which they are happening is the number of interactions that are happening every second. And so that interaction probability is just going to be equal to that 10 to the 6th reactions per second divided by this 10 to the 10th neutrons per second. And so this then equals 10 to the minus 4. And so the percent likelihood that any neutron is going to experience some interaction in this with these numbers is a 0.01%, basically 10 to the minus 4. So I could define that then as my reaction rate, that was 10 to the 6th, divided by 10 to the 10th, which is going to be NBVBA. And we also know that R is going to be sigma NBVB N A delta X. So my probability could be expressed as sigma N delta X. If I know the cross-section, if I know this cross-section we've been talking about, sigma, N is the number density of the atoms, so I can figure that out. And I know how thick the parameter is, and so I know from that information alone, I know what the probability is that there's going to be that type of interaction. And this sigma that we're talking about in this example and in the lecture up until now, we've set the stage with a discussion of scattering, but in reality it can be any event at all, including fission, and we'll see in just a minute of all the different types of events that we could consider. But for each and every one of those events, there is a cross-section tied to that. So there's a cross-section that tells me what the likelihood is that I absorb that neutron. I have this target that I'm trying to have the neutron experience a scattering event, but sometimes I'm going to absorb that. And so some isotopes are going to have a higher propensity to absorb the neutron than to allow it to scatter. But I would use the scattering cross-section if I want to look at the probability of scattering, and I look at the absorption cross-section if I want to look at the probability of a neutron being absorbed. And you'll also see there's a total cross-section, and so that represents all the subtypes of interactions. Every type of interaction has its own cross-section. And again, we'll look at that online here in just a minute. So let's now find the cross-section. To find that cross-section sigma, we'll just use this expression here. So this is going to be R divided by N B VB N A delta X. So I've already got these. I should have put them in a different order here. Because these three here I already got. That's going to be 10 to the 10th. And I know this one is going to be, what was it, 10 micrometers? 10 micrometers, so that's going to be 10 times 10 to the negative 4th centimeters. R, I've got R, I know that's going to be 10 to the 6th per second. And so the only thing I don't know in this case is this N. And so I need to figure out the atom density of aluminum 27. That's what I need to figure out. So this should be units of number of atoms per volume, so number of atoms per centimeter cubed. So if we go and look up the mass of aluminum 27, then we'll find out that it's going to be 26.981538 AMU. And we can go to any nuclide chart, or we could go to the functions that we've made to look this up. But that's a unit of mass, and what that represents is the AMU per atom. Every atom has that mass. Right? That's the ratio there. And I want to note that the density of aluminum is going to be 2.7 grams per centimeters cubed. And then as just a side note here, so you may have noticed this or may have not, but let's make sure that everyone's clear on this. 1 AMU, if you remember back from an earlier lecture, this is going to be 1.6605 times 10 to the negative 24th grams. Right? An AMU is a unit of mass, a gram is a unit of mass. And if I take that 1 gram and I divide it by 1 mole, then I'll get 1 gram divided by 6.00 or 6.02. Avogadro's number here, 2 times 10 to the 23rd atoms. And so this is going to be equal to we want to know how many grams per atom. So this is going to be equal to, if you do that math, you find out it's 1.6605 times 10 to the negative 24th grams per atom. And so if we look at the grams per mole, which is typically what your mass numbers are given in, so gram per mole is going to be equal to AMU per atom. And so because I can look up AMU, or I have it just spit it out, I just need to recognize the fact that these units are identical. AMU per atom is identical to gram per mole. And so if I know that the AMU up here for my aluminum is this many AMU per atom, I also know that it's going to be equal to 26.981538 grams per mole. And so I can use that. That's what I'm going to use to calculate. This is the thing to remember. That's what I'm going to use to calculate my atom density in the aluminum. And so my atom density is going to be the density of the aluminum multiplied by Avogadro's number divided by the molar mass of this aluminum, and so that's going to be equal to 27 or 2.7 grams per centimeters cubed. Avogadro's number is 6.022 times 10 to the 23rd atoms per mole, and then divide by the molar mass, which is 26.981538 grams per mole. It was AMU per atom, but we know that those two units are exactly the same. So we've got moles canceling out, we've got grams canceling out, and so we're left with atoms per centimeter cubed. And what we find there is that N is going to equal 6.0261 times 10 to the 22nd atoms per centimeter cubed. And so sigma, our cross-section, is going to equal 10 to the 6 reactions per second divided by 10 to the 10th neutrons per second multiplied by my atom density now, 261 times 10 to the 22 atom per centimeter cubed, multiplied by the thickness, right? The thickness of the slab. So that's 10 times 10 to the minus 4 centimeters. So the units of this that we're expecting is going to be a unit of area, and we find out that sigma is going to equal 1.6594 times 10 to the negative 24th centimeter squared. So what does that mean? It's unit of area, but it's also related to the probability that an event's going to take place. You can only take this analogy so far, but it is useful in many contexts, I guess, to think of this on the order of the size of the nucleus itself. You got the atom that's this big and the nucleus that's this big, and we're trying to hit that little target. And so how big is that target? But because we get tired of writing 10 to the minus 24, this is going to be 1.66 barn, where 1 barn equals 10 to the minus 24 centimeters squared. Okay, so that's our cross section. Let's take a look at, just to give you some initial looks at other data that's available in many of the sources and resources that we've already talked about for nuclide data. I'm going to use the Korean web page, the Kyrie web page here. But you're going to find the same information on Brookhaven's and all the other ones that we have discussed so far. And I'll bounce back and forth between them throughout the semester, but for this example, I'm going to use this. I find it as far as visually, I find this one easiest to use. But so I come in here, I'm going to type the nuclide name. The nuclide in this case is aluminum 27, was it? Yeah. Aluminum 27. And I've got the atomic mass, which I already had for this problem. I've got all these other things we looked at, binding energy. But down here, which we haven't really touched, we've got all these evaluated nuclear data. And ENDF, evaluated nuclear data file, that's what this represents here. And so this down here, I believe this is the one from Japan, or maybe this is the one from Japan. But each set of researchers from different countries that are doing these experiments to capture the cross-sections and that sort of thing are going to publish their data and make it available to everyone else. So it's the same underlying data that you're going to see in all these different resources and tools, but I generally just use the most up-to-date version of ENDF, the NDF files. So this is 8.0, 7.1, 7.0. So I'll come in here, I click on cross-sections. So for aluminum 27, I've got all sorts of cross-sections to look at here. I can look at the total cross-section. Let's start with that one. As I click plot, I see the cross-section down here. You see that it's a function of that neutron energy. And then the y-axis here is in units. It says B, but it's units of barn. We were looking at the elastic cross-sections earlier today. I could look at that one. So it updates my plot. And I could down here, I could add this to the viewer. You see it appears right here. And then let me go back to the total cross-section. And I want to add that to the viewer. And if I open up the viewer, it opens up a new tab, and I can see these side by side. And so this blue one here is you see NEL. So N, the neutron coming in, an elastic collision. And so this cross-section represents the value in barns for that event to take place, for an elastic collision to take place. And you see the red one here is my total. So that's looking at everything from elastic collision to absorption to fission to any event that we have data that we've collected data for. We add all those together to get our total cross section. And so what you see for this right here for aluminum, all the way from about 0.1 EV, or definitely 1 EV, all the way up to maybe 1 MeV. It's not any different. So what this means is that the total cross section is almost exclusively explained by the elastic collision cross section for aluminum 27. And you'll notice that for each of these, I've got this. This is a log scale. Keep in mind, but I've got this. This is called the 1/V range at the very low energies. I got this over here is called the resonance region. And for this region here, all the way from 1 EV up to maybe even 1,000 EV, so a kilo EV, KeV, I've got almost consistently uniform cross-section, and again, my total cross-section is almost entirely explained by the elastic collision cross-section. And you see that I'm here at 1 e to the 0, so that's 1, this is 2, I'm right around 1.6 or so barns. And so that data from the previous problem is actually spot on with what we would expect for aluminum. And so, I input data in there that I knew would work for aluminum. But in general, what you're going to do is not know the reaction rate, you're going to go to these files. You're going to find for your kinetic energy, for the neutron that is the kinetic energy of the neutron that you are considering, look up the cross section, and now you can determine what the reaction rate is. And I can go back here and let's go back here actually. Let's look up U-238. And let's come down here and look up let's clear these plots first of all. Let's look up the fission cross-section. So here's the fission cross-section for U-238. That's what it looks like. Again, I got that 1 over V range. I got this resonance region. But what I want to do is compare that. I'm going to add that to the viewer. And then let's compare that to U-235, which is really what we want. And so for fission. So let's come down here and let's look at its fission cross-section. Make that plot. And I'm going to include this in the viewer, and let's open this up again and compare the two. Okay, it didn't do a very good job with the ranges. Let's take a look over here. Let's make this 1 e to the minus, let's do minus 5, and this will be 1 e to the 4. Let's try that. Okay, we need to go a little bit lower. The 2 orders of magnitude. So the bottom one here is the U-238, and the top one is the U-235. And so you can see at high energies, right? Here's 1 MeV coming out of that fission event. Whether it's U-238 or 235, I have a relatively low fission cross section. It's not until I slow them down that I start to see this at least 2 to more orders of magnitude, and I mean this is why we want 235 instead of 238, because the fission cross section is orders and orders of magnitude. I mean, we're talking about 6 to 7 orders of magnitude higher for the U-238 than it is for the U-230, or higher for the U-235 than it is for the U-238. So we can go back and look. Let's see what my total is. This is 235. Let's see what the total cross-section is for U-235. Let's add that. So you can see that in this lower energy spectrum, my total cross-section for U-235 is almost exclusively explained by the fission cross-section. Just like in aluminum-27, it was almost exclusively described by the scattering cross-section. U-238, it wants to fission. Just give me a neutron, and of all the different interactions I could have, I'm almost entirely going to undergo fission. Now, there is small chances to have other types of interactions. It's not exactly the same, but it's almost exclusively explained by that fission. So let's take a look at the total in U-238, actually, just as a comparison. Plot that one, add it. And by the way, you can just download all this data here. So, okay, so here's the total. The magenta curve here is the total for my U-238. So it's, what is that, 5 orders of magnitude or more in some cases. The likelihood of fission is almost inconsequential to whatever else is going to happen. So we would, if we were unsure what would happen, then we'd need to dive in. Let's look at, this is 238 still, yeah. Let's look at the elastic cross section. So now we're starting to see that the elastic cross section is one of the dominant ones, right? Compare this gold one to the magenta one, and you see, especially in this range of about 1 eV or 0.1 MeV, or 1 eV or 0.1 eV, I am almost exclusively, all the interactions that could take place, it's almost always going to be an elastic collision for U-238. Anyway, so you have all these available to you. You can take any of these and you can get the data. It's not going to be the entire one, it's whichever one you're looking at here. So I can get the data and I can copy and paste this and use it as a text file. So this is my EV and my cross section in Barnes. And so I could just plot it myself or include this into some other application, whether it's a MATLAB script or a Python script or something. But this is a lot of data, and you're gonna keep scrolling down. So it's better to hit Control A and once it's done loading and copy and paste it in that way. Okay, we will talk quite a bit more about cross sections and the different types of cross sections. We'll talk about something that's called the macroscopic cross section. But for now, this is just kind of a preliminary discussion and kind of setting the stage for other cross-section discussions in the future. And you want to be comfortable using units of Barn, 10 to the minus 24 centimeters squared. And just like it's the third of the trifecta for nuclear measurements. So you got AMU, EV, and now Barn. So that concludes this lecture. We'll see you soon for lecture 8.